You can see from the last lesson how easy it is to get caught up in all the details. So to start off this lesson, I want to just review so that we are on the same page. What does it mean for a function to be differentiable at x equals a? So here I have the function, and you can pick any value here, x equals a. What does it mean that a function is differentiable at x equals a? That's calculus differentiability. What does it mean? Well, it simply means that at that point, we have an instantaneous rate of change. At that point, we have a slope. We could say at that point, we have the tangent, and that tangent has a defined slope. That makes it differentiable. So if the function itself has a slope, does it have a slope here? Oh, yes, it does. That tangent happens to be horizontal, and the slope of that is 0, and 0 is a real number, so it is differentiable. So differentiable at a point simply means it has a slope at a point. It simply means that there is an instantaneous rate of change at that point. We also discussed times when the function was not differentiable. Here, yes, it's differentiable. Yes, there's a slope. Yes, it's differentiable. But sharp corner, no. The function is not differentiable at x equals a. Sharp transition, not a smooth transition. And then we continue on. Yes, there's a derivative. Yes, there's a derivative. Yes, there is a derivative. It is differentiable here. Maybe horizontal tangent. Yes, 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 yes. And then, of course, we get over here and we say, no, this looks like perhaps it is a cusp, an extreme corner. F is not differentiable at the cusp. And then you can see here that the function at C is not continuous, and when the function is not continuous, it cannot be differentiable. But everywhere else on this function, with the exception of A, B, and C, everywhere else has a slope, so everywhere else the function is differentiable. Okay, example number 1. Now, example number 1 could actually serve as a warm-up. I feel like you should be able to answer all of these questions. In each one, it wants us to find or estimate a given derivative. So in part A, can we estimate f prime at 1? So we come over to x equals 1, and this pink circle lies on this gray portion of the graph, and it said gray is a line segment, and since it's a line segment, it's a linear portion of the graph, and so we simply need to calculate the slope. In this case, the slope would be -2. We calculate here the change in y over the change in x, the rise over run. We rise 2, we run 1. In part B, we want to estimate or find the slope at the point -1. Well, you could kind of eyeball that in your mind, draw a tangent and figure out what the slope of that tangent is. A more standard way to do this is to pick two coordinates, two integer coordinates that are present. So here's one of them, and here's the other one of them, and find the slope between those 2 points to estimate the derivative, or estimate the slope at the point inside. So this would be f at 0 minus f at -2 all over 0 minus the -2. If we compute that, then we're going to get 4 minus 6 over 2, and so it estimates to be -1. Now, if, again, you were to eyeball this, you might take a tangent in here. Ooh, tough to do. And compute that slope. And I think by eyeball estimation, I think you'd get also pretty close to the -1. In part C, they want to know what is the slope here, what is the derivative here, and I hope you clearly see that that one does not exist. There is no slope. We have a corner here. How about at x equals 0? How about here? Well, what I would like you to see is to the right of this, we had the line segment, and that had a slope of -2. and then this parabolic portion comes in, and it appears, at least appears, that we have a smooth transition. So since it's smooth, it's the same slope on the right or left. So I'm going to estimate this to be -2 and make the note that it appears to have a smooth transition at x equals 0. In part E, we want to determine or estimate the slope at x equals 8. Well, that to me definitely looks like it's going to be 0, because it appears that the tangent to f at x equals 8 is horizontal. Now, I'm not guaranteeing it, that's why I'm estimating, but it looks like the tangent line here is horizontal, and a horizontal line would have a slope of 0. Let's take a look at f. At f, it wants to know what is the slope at x equals 10. If I utilize the standard estimation, then we have to pick two integer points, one to the right, one to the left, and then compute the slope between those 2 points. And so f prime of 10 would be f at 12 minus f at 8 all over 12 minus 8. And so what do we have? -4 minus 0 over 4. So it looks like -1 is the standard estimate. I'm going to guess if I did an eyeball estimate of this, that's a pretty good tangent. It looks like it's going to be something different than -1. So perhaps you have an eyeball estimation, approximately, I don't know, -2, -1.5, something like that. Okay, let's take a look at G. Here, x equals -9. Well, that's on a line segment, so we got to do a little bit of rise over run. So this one is equal, not approximately, this is equal to 1 over 6. We calculated change in y over change in x. Okay, h at 13. Okay, 13 is also on a line segment, so we can compute it. I can also see that it's simply 0 because we have a horizontal segment, and horizontal lines or segments have a slope of 0. Next, we have I, which wants us to tell us what the slope is at this endpoint. Now, endpoints, this is new to you. At an endpoint, it doesn't have a side to the left, it only has a side to the right. And so what we say here is the answer is equal to 1/6. It's going to be the same slope as it was to the right. This is an important thing to write here, that endpoints are differentiable as long as the slope exists from one direction, one side or one direction. So see, the slope was 1/6 on one side of it, and it came in to be 1/6 from the right-hand side, and so we say the endpoint also has a slope of 1/6. There is nothing here on the left, but since it's an endpoint, that does not matter to us. Lastly, we want to determine where we have horizontal tangents. Let's see, it looks like we have not quite at -2, but a little bit to the left of that, we have a horizontal tangent. It looks like we have a horizontal tangent here. And then we have horizontal tangents for all points basically inside this range. So let's see how we're going to write this. We're going to say we have a horizontal tangent when x is approximately, let's go with -2.25. There's no one exact right answer here. We're going to say x is approximately 8. And then we're going to be a little bit more careful over here. We're going to say x belongs to, now I'm going to use a parenthesis for 12. Can you guess why I have a parenthesis? Can you guess why there's not a horizontal tangent when x equals 12? Well, there's a corner, and there is no slope, so there cannot be a horizontal tangent. But at 14, because there is an endpoint, it takes on the slope to the left of it. So there is a horizontal tangent at 14. Now, boy, that's a little nitty-gritty, but I wanted to be technically correct in this. Example number 2. First thing it asks us to do is to connect these dots with a smooth curve. And I'll just connect them like this. Boy, that's very jittery, isn't it? And I don't have to be too careful. Okay, we connected them with a smooth curve. Now, we don't know for a fact that the function has all that. All we know is we have these ordered pairs along the way. And I'm just going to kind of pick them out a little better. All right, so eyeball estimation. Quite frankly, I'm not all that interested in eyeball estimation. It's not a standard method that's allowed on AP. You might give it a try, though. Draw a tangent. We need an eyeball estimation for f prime of 1, and we also need an eyeball estimation for f prime of 2.5. So that means at 1, we draw tangent the best we can and predict its slope, and then at 2.5, draw tangent and predict its slope there. You got to be careful because of the scale. This goes 10, 15, 20, while these go by increments of a half. So you'd have to kind of factor that in with an eyeball estimation. But I do want to emphasize that eyeball estimation is not something that they will allow. There's going to be only the standard way. Now, the standard method of estimation is what we discussed in the last problem. If I'm trying to figure out what the slope is or estimate the slope at 1, I want to pick 2 points, one to the left, one to the right, and find the slope between those two coordinates. Now, I call this the average on a nearest neighborhood method, and I want to explain why I call that. See, we're trying to compute the instantaneous rate of change. But instead of finding the instantaneous rate of change, I find the average rate of change, but I find the average rate of change on a small neighborhood. It would not serve me well to find the average rate of change between the two furthest points, because that slope is clearly a large positive. But if I do a small neighborhood, so pick 2 points, one to the left, one to the right, and compute its slope, then I have a good estimation, and that's going to be our standard estimation. I can use the chart above as well. So if I'm trying to compute the slope at 1, I pick 2 points, 1 point to the right, 1 point to the left, and find the slope between those 2 points. So let's do that. So f prime of 1 is approximately f at 1.5 minus f at 0.5 all over 1.5 minus 0.5. And so we use our chart to figure that this was negative 15 minus negative 15 all over 1, and that comes out to be 0, which is probably what you eyeball estimated the derivative to be at 1. So that one was fine. This other one, however, is a little harder to do with the eyeball, so we certainly want to try doing this average on the nearest neighborhood. So here's 2.5, here's to the right, here's to the left, and so we're going to have f at 3 minus f at 2 all over 3 minus 2. So what does that give us? 0 minus a negative 12 all over 1. So it turns out we estimate using the standard or average on a nearest neighborhood method, we estimate the slope to be 12. Here we estimated it to be 0.